All right, hi everyone, and welcome to Unit 2. We're making progress. It's going to be great. Today we're going to kick off by talking about normal distributions and kind of what those are. But the whole goal of this unit at the very end is going to be able to compare data values to its own population that it's in or across other populations. So kind of in light of last unit, comparing data distributions. All right, let's go. This video in particular is going to be talking about how we simplify data distributions, and in particular, density curves are what we're going to use to do that. All right, skim on down the page with me. We're going to go over to page 3. Mine printed a little bit bad, but hopefully yours is not. That's kind of be down here. One way to simplify data distributions, or what a data distribution even is, that's just the collection of data. And we already talked about most data distributions have like vast amounts of data, lots of data. Okay, so it's not just like a data set with 10 things. We're talking about hundreds or thousands of things. So today, in light of that, we're going to talk about density curves. What a density curve is it is a curve that approximately follows the top of the data when data is in a relative, remember relative kind of means percent, of frequency histogram. Okay, so all that means is everything's in terms of percent. So if you kind of skim down here and look at this one, you'll notice on the sides, this is a percentage version versus just straight up numbers. And you kind of see that that's a histogram with lots of bars all across. And so what this is allowing us to do, it's going to kind of oversimplify because there are so many bars of what's going on. It's just going to kind of simplify the picture. So it's going to help us give a quick reference for our shape, center, and spread. It's not going away for the rest of the year. And so here's a density curve that kind of follows the top of that histogram, kind of lets us see here. And if we were to describe that, we would say it probably looks pretty symmetric. Versus this one as well is also pretty symmetric following the top of this. Maybe a note that you make to yourself is not all density curves are curvy. Density curves are curvy. So here, curvy. Which you can kind of see that here. It comes to like a nice point. Or you could have even, just to the same sort of point, you could have a histogram, density histogram, where all the bars look kind of similar across or uniform across, and the density curve for that would be looking something like that. That's not curvy either. We also see density curves here where they follow, where we've got a skewed right density curve, or even here kind of a bimodal one, right? So density curves just kind of simplify the overall picture. Now, some things that we need to know about all sorts of curves is that the total area that the data kind of spans or takes up is always 1. All right, because we're talking about percent, it's like 100% of the data, right? So the area under the curve, or section of the curve, is equal to the percent, or maybe you think of the proportion of the data that fits between the section's endpoints. Okay, what I mean by that is if we look at this one down here below, we have got a density curve going on over here. It says the age of when their first word is spoken. So if you look, the majority of kids are kind of speaking their first words between kind of 1 and 2.5, and then it kind of spaces out where some kids are talking a lot later. That is representing 100% of the data. If we just look at just this little section right here, this is saying that 40% of the area of that curve is right there, and that is between 2 and 3. We could also say that 40% of the data is between 2 and 3. So 40% of kids speak their first words between 2 and 3 years old. We could also say that 40% of children, which is what I just said, putting some context to it, is between 2 and 3. So the data, but so happens to be about children, right? So all density curves have an area of 1, kind of talking about 100% of the data, and the area is proportional to the percent of that data. All right, moving on here, a couple other things that we should know about density curves are really just this kind of top part. One thing that we could get a quick reference is the median. So the median is located on the horizontal axis where a vertical line could be drawn to split the data in half. So, for instance, if we rolled back up here and I wanted to split the data in half for this, I could kind of eyeball it and say, all right, it kind of looks like the halfway mark is maybe in here. That would be where our median is. Or I could say, hey, the half looks in here, or maybe halfway would be here, right? Those would be all of our medians or middle points. Versus the mean is going to be the location on the horizontal axis where the density curve would balance itself. So if you could kind of imagine putting your finger on a certain spot, where would it balance? So here, I think it would still kind of balance maybe here. That's where your mean would be. Your mean would be here, your mean would be here. I would probably have to be over here to kind of keep it balanced. But that's a good way to give yourself a quick, just a quick reference for where the mean or the median are. So looking at this one, again, maybe we'll just label some of this. This right here would be where we split the data in half. So this would be the median, where we'd have 50% of the data over here and 50% of the data over here. Or maybe you could say that the area under the curve is 0.5 on this side, and the area under the curve on this side is 0.5. All right, versus if we wanted to find the median or the mean part, if you tried to balance it on here, like it's not going to balance if you try to put the mean and the median in the same spot. So what happens is, just like we talked about last unit, whenever you have skewed data or outliers, the mean gets pulled towards those, right? So our mean would end up being somewhere a little bit further over in here, right? It gets pulled, this one's skewed right, so it gets pulled to the right, and so this would be where the mean is, the balancing point. It would have to probably be scooted over just a little bit in order to balance it out. Are we okay with this? So this would be balance point. So kind of deals with last unit. Okay, and this part would still be your median, but they're not equal to each other. And also last unit, we talked about if the data was symmetric, we know that the median would be about the same as the mean, right? We talked about that last unit. So looking over for this set, the mean and the median would be kind of in the same spot. It's symmetric, right? So they kind of be on top of each other. Same with here. This data is symmetric, so they would be on top of each other. So the median would be equal to the mean. So that's just, again, if you wanted a quick kind of remembrance from last year, quick reference for where the mean and median are on a density curve, you could kind of just glance at it. All right. Continuing on, now that we know a little bit about density curves, just about them, that their area is proportional to the amount of data underneath of them, and that it's kind of an oversimplification. You kind of can look at it and feel good about it. There is a particular type of curve that we're going to work with, density curve this unit, and a type of density curve that we're going to deal with, and it's going to be perfect, and we're going to love it for the rest of the year, are these things called normal curves. So normal curves are special in the thought of that they have a couple of attributes. So this right here is a normal curve. One of the things that we should notice about it is that it is a symmetric curve. Symmetric. Not only is it symmetric, we say that it is single peaked. And if you kind of go back up here, this one, this thing is symmetric and single peaked. So it's got one other attribute, and the other one is that it is bell-shaped. So if you kind of have all three of those things happening, you've got a normal curve. It has to be all three. Now, interesting thing about these density curves is they actually extend from negative infinity to positive infinity. So they just kind of keep going. But if you look over here, there's like almost nothing underneath of it, right? And because it's a density curve, but it's a type of density curve, right? It still has a total area of 1 underneath those axes. So kind of interesting. We're going to talk a little bit more about this in the next video. Actually, let's see, where are we at? So at this point, we've talked about density curve functions. A normal curve is a type of density curve function. And I guess we'll just go with this for a second too. The normal curve function. So not only is it just a beautiful, just kind of curve and it has those attributes, it's actually a mathematical thing. So a lot of data is approximately normal. So let's just kind of look at this. A normal curve function. Just like if you had linear data, you could say, all right, what makes that line is y equals mx plus b. Or if you were interested or focused with a quadratic function, y equals x squared, or any of these others, a normal curve actually has a function too. This is it. It's super ugly and kind of scary looking. And there's only a couple of things that you need to know from there, and we're just going to highlight them. All right, one of the things that you need to note is that the mean is hidden in the formula. It is in this upper kind of portion. And the other thing that you need to know is where the standard deviation is located. It's kind of the bottom of that fraction. We're off here to the side. We'll kind of come back to that later, but just know, not only is it just a pretty curve that happens to look like these three things, it actually is made up of an algebraic function. All right, we're going to end with that, and we'll get right back into normal curves.